Hello, thank you for coming to see my video. My name is Sangyoon. In this video, I will present a method for generating haptic motion effects for multiple articulated bodies. 4D content is an extremely immersive form of entertainment, providing multisensory effects such as motion, vibration, and wind effects with audiovisual content. 4D applications are getting more popular and common. One of the most frequent for the effects is the object-based motion effect. In this case, a motion chair applies physical movements to the viewer's body to emphasize the movements of an interesting object on the screen. In this work, we present an automatic algorithm to generate object-based motion effect when we have multiple articulated bodies in the scene. A rigid body object can freely translate and rotate in 3D space. In other words, it can move with 6 degrees of freedom. In contrast, an articulated body is made up of many joints and links, so it can move with higher degrees of freedom. Also, multiple articulated bodies have much higher degrees of freedom. We watched many 4D films and found that the motions of object parts and the motions of multiple objects were combined and expressed as a motion effect. However, the motion chairs in the 4D theaters can move with only 3 degrees of freedom, and their motion ranges are very narrow. Therefore, it is very difficult to make a motion effect for articulated bodies. Motivated by this, we set our research goal as designing an automatic algorithm to generate motion effects that express the motions of multiple articulated bodies within the narrow motion range of a motion chair. Before going into detail, I'll show you a short demonstration. To express a high degrees of freedom motion with 3 degrees of freedom motion, we introduce the concept of motion proxy. A motion proxy combines many motions in the scene into a single movement of a motion chair. Our algorithm generates the motion command in 3 steps. First, it combines the motions of object links into an object motion proxy. Second, it combines the object motion proxies of all the objects in the scene into a scene motion proxy. Finally, the scene motion proxy is converted into a motion command through a motion queuing algorithm. The motion queuing algorithm makes the motion commands to reproduce the movement of the motion proxy within the motion range. To determine the best combinations of the motions, we conducted 2 studies. First, we conducted a study on a single articulated body. In this study, we designed several link weighting methods and evaluated them through a user experiment. We designed 3 methods: size, momentum, and single. Size reflects the motion of a larger link more. Momentum emphasizes the motion of a faster or larger link. Single expresses the motion of one link. These are the videos and the trajectories of the motion commands used in the user experiment. It visualizes the motion proxies calculated by 3 methods as a motion of a point. Size mainly focuses on the motion of the torso, the largest part. Momentum follows the fast motions of the arms. In this video, the motion of the torso is reflected in the single. Then we conducted a user study to compare the 3 methods. We prepared 12 videos showing the motions of a single articulated body. While watching each video, participants experienced 3 sets of motion effects: size, momentum, and single. Then participants rated 6 measures: harmony, causality, fatigue, distraction, detail, and preference. In the results, momentum showed the best performance in terms of harmony, causality, detail, and preference. Then we conducted a study on multiple articulated bodies. In this study, we designed several object weighting methods and evaluated them by performing another user experiment. We designed four methods: additive, uniform, salient, and single. Additive reflects the motion of a faster or larger object more. Uniform expresses the motion of all objects in even proportions. Salient captures the motion of the fastest or largest object at each moment. Single expresses the motion of one object. These are the videos and the trajectories of motion commands used in the user experiment. You can see that additive and salient capture the motion of a fast object. Uniform expresses the average motion of two objects. The 2 points of a single follow the motion of each attacker and victim. By conducting a user experiment, we compared the four methods. We used 8 videos showing the attacker and the victim fighting each other. For each video, participants experienced 5 sets of motion effects, then they rated scores for 6 measures, as in the previous experiment. As a result, additive, salient, and single, which expresses the victim's motion, showed better performance than the others. We expect that additive and salient will be more advantageous for the scenes where many people fight each other, because additive and salient emphasize more important object motions at each moment. This is the conclusion. This work is the first to propose an automatic algorithm to generate object-based motion effects for articulated bodies. Also, in the paper, we share design guidelines learned through our research. However, this work has some limitations. We did not extract the motion information automatically. Also, we did not test our algorithm for various cases, such as more than two objects and camera moving scenes. We expect that our research can help the production of 4D effects. This work was supported by the Samsung Research Funding and Incubation Center of Samsung Electronics. This work is done with my collaborator Jaejun Park and my advisor Seungmoon Choi. This is the end of my talk. Thank you for watching it.